Number systems. In this video, we will introduce the decimal, binary, octal, and hexadecimal number systems. What is a number system? A number system defines how numbers can be represented. The one we are most familiar with is the decimal number system, which is a base 10 number system, meaning it has 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. To further show why we call this number system a base 10 number system, we're going to use a table. In the top row of this table, I'm going to write 10 to the power 0. Then in the top of the next column, I will write 10 to the power 1. Then at the top of the next column, 10 to the power 2. Then at the top of the next column, 10 to the power 3. Then at the top of the next column, 10 to the power 4. So on and so forth. I could go on doing this for an infinite number of columns, but it's not needed for me to make the point that I'm trying to make. So for this video, I'm just going to stop at 5 columns. When I simplify each of these exponents, these are the values I get: 10,000, 1,000, 100, 10, and 1. Then for our first example, I'm going to select a random one-digit number. For this example, I'll select 8. For each of our examples, the rightmost digit for each number will always go in the rightmost column of the table. Since 8 is the only digit in this example, that means 8 will go in the rightmost column. For the other blocks that are still empty, just assume that we put 0 there. Next, we're going to multiply the top row by the bottom row, then add up each column. Since any number multiplied by 0 equals 0, we can pretty much cancel out the first 4 columns and focus just on the 5th column, 1 times 8. In other words, 8 can be represented as 1 times 8. The usefulness of this table will be more easy to see with a 2-digit number. So for our next example, we're going to select a random 2-digit number. For instance, 47. As stated before, the rightmost digit goes in the rightmost column, followed by the next rightmost digit, which is 4. Based off this table, we can now see that 47 could also be written as the sum of 10 times 4 and 1 times 7. Now let's select a random 3-digit number. For example, 863. Once again, the rightmost digit goes in the rightmost column, followed by the next rightmost digit, and then the digit after that. 863 could be written as the sum of 100 times 8, plus 10 times 6, plus 1 times 3. Now let's select a random 4-digit number. For example, 7,493. Once again, the far rightmost digit goes to the far right column, followed by the next rightmost digit, followed by the next rightmost digit, followed by the next rightmost digit. 7,493 can be seen as the sum of 1,000 times 7, plus 100 times 4, plus 10 times 9, plus 1 times 3. And now for our last example, we'll pick a random 5-digit number, 98,376. Rightmost digit goes to the rightmost column, followed by the second rightmost digit, followed by the third rightmost digit, followed by the fourth rightmost digit, followed by the fifth rightmost digit. The number 98,376 can be seen as 10,000 times 9, plus 1,000 times 8, plus 100 times 3, plus 10 times 7, plus 1 times 6. As stated earlier, the decimal number system is the system that we as Americans are all pretty much familiar with, but as computer scientists, it is not the only number system we must be familiar with. We must also become familiar with the binary number system. The binary number system is a base 2 number system, meaning it has only 2 digits, 0 and 1. We can construct a table for the binary number system the same way we did for the decimal number system, but with 2 as our base instead of 10. Meaning, for the first rightmost column at the top, we're going to put 2 to the power 0, followed by 2 to the power 1, followed by 2 to the power 2, or 2 squared, followed by 2 to the power 3, or 2 cubed, followed by 2 to the power 4, so on and so forth. We could go on forever if we wanted to, but for simplicity, we'll just stop at 5 columns for this video. When I simplify each of these exponents, I get the numbers 16, 8, 4, 2, and 1. Now, with this table, anytime I'm given a random binary number, I can convert it to decimal using this table. For example, the binary number 1010 base 2. Notice I put a subscript on this number. I put the subscript 2 to indicate that we're looking at the binary number 1010, not the decimal number 1010. 1010 is not what I'm looking at. I'm looking at the binary number 1010, and I want to convert it to decimal to see what this number means in decimal. I can use my table to do that. I start by taking the rightmost digit, which is 0, and putting it in the rightmost column, followed by the second rightmost digit, followed by the third rightmost digit, and the fourth rightmost digit. Now, I'm going to multiply the top row by the bottom row and add up each column. When I do that, I get 8 times 1, plus 4 times 0, plus 2 times 1, plus 1 times 0. When I simplify that, I get 8 plus 0 plus 2 plus 0, which equals 10. Thus, the binary number 1010, when converted to decimal, is 10. Let's do one more binary example. Suppose we get 5 ones. What is 5 ones in binary converted to decimal? Well, once again, the far rightmost digit goes to the far right column, followed by the next rightmost digit, and the next one, and the next one, and the next one. Since we have 5 ones, the bottom row of our table will simply contain 5 ones. Then, to convert it to decimal, we're going to multiply the top row by the bottom row, then add up each column. When we do that, we get 16 times 1, plus 8 times 1, plus 4 times 1, plus 2 times 1, plus 1, which simplifies to 16, plus 8, plus 4, plus 2, plus 1, which simplifies to 31. The next number system we must be familiar with is the octal number system. The octal number system is a base 8 number system, meaning it has 8 digits, 0, 1, 2, 3, 4, 5, 6, and 7. The table for our octal number system will be constructed the same way we did for the other 2 number systems, but this time 8 will be our base. So for the far right column at the top, we're going to put 8 to the power 0, followed by 8 to the power 1, followed by 8 to the power 2, followed by 8 to the power 3, and followed by 8 to the power 4. Once again, I could go on forever, but for simplicity, we'll simply stop at 5 for this video. When I simplify these exponents, I get the values 4,096, 512, 64, 8, and 1. Now let's select a random octal number and see how this table can be used to convert that number to decimal. For example, 475 base 8. Once again, I put the subscript 8 to indicate that we're looking at the octal number 475, not the decimal number 475. We're looking at the number 475 base 8. Now, what is this number when converted to decimal? Well, we start by taking the far right digit, the rightmost digit, putting it in the far right column, followed by the second rightmost digit, and then the third rightmost digit. Next, we're going to multiply the top row by the bottom row, then add up each column. When we do that, we get 64 times 4, plus 8 times 7, plus 1 times 5, which simplifies to 256, plus 56, plus 5, which simplifies to 317, decimal. Let's do one more example for octal. Let's do 21537 base 8. Once again, this is an octal number. We're not looking at 21,537. That's a decimal number. What we're looking at is 21537 base 8. What is this number converted to decimal? Well, we'll start by taking the far right digit and putting it in the far right column, followed by the second rightmost digit, followed by the third rightmost digit, then the fourth rightmost digit, then the fifth rightmost digit. Next, multiply the top row by the bottom row, then add up each column. When we do that, we get 4,096 times 2, plus 512 times 1, plus 64 times 5, plus 8 times 3, plus 1 times 7, which simplifies to 8,192 plus 512 plus 320 plus 24 plus 7, which simplifies to 8,777. The last number system we're going to discuss is the hexadecimal number system. The hexadecimal number system is a base 16 number system, meaning it has 16 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the letters A, B, C, D, E, and F. Now you might be wondering, what do the letters mean? Well, the letter A represents 10, the letter B represents 11, the letter C represents 12, the letter D represents 13, the letter E represents 14, and the letter F represents 15. Now that we know what the letters represent, let's construct our table. The table will be constructed the same way it was for the other three number systems, except now our base will be 16. So in the top row, in the far right column, we'll have 16 to the power 0, followed by 16 to the power 1, followed by 16 to the power 2, then 16 to the power 3, so on and so forth. Once again, I could go on forever if I wanted to, but for simplicity, I'll stop at 4 columns for this video. When I simplify these exponents, I get the values 4,096, 256, 16, and 1. Now, let's select a random hexadecimal number and see how we can use this table to convert it to decimal. For example, 3AC base 16. Once again, the rightmost digit, put in the far right column, followed by the second rightmost digit, then the third rightmost digit. Now remember, the letter A represents 10, and the letter C represents 12. Knowing that, let's multiply the top row by the bottom row, and then add up each column. When we do that, we get 256 times 3, plus 16 times 10, plus 1 times 12. Once again, recall, A represents 10, C represents 12. When I simplify that expression, I get 768 plus 160 plus 12, which simplifies to 940. Let's do one last example. Let's do a 4-digit hexadecimal number. Let's do F20E, base 16. Once again, the rightmost digit goes in the rightmost column, the second rightmost digit goes in the second rightmost column, the third rightmost digit goes in the third rightmost column, and the fourth rightmost digit goes in the fourth rightmost column. Remember, the letter F represents 15, and the letter E represents 14. With that in mind, let's multiply the top row by the bottom row, and then add up each column. When we do that, we get 4,096 times 15, plus 256 times 2, plus 16 times 0, plus 1 times 14, which simplifies to 61,440, plus 512, plus 0, plus 14, which adds up to 61,966.